Why would you just take part of it?
United States of America, and to the republic which stands one nation, under God, indivisible, with liberty and justice for all. Please stop text Bixby to 88709 for help from professionals. Completely free and confidential. 24/7 texting service is totally anonymous and it's your schedule. To seek help, tips, and encouragement, give it a try. Please stay tuned for more student out. Have a good day, Skipper.
Do you know what's happening next Tuesday evening in Black Box? I don't know what's happening next Tuesday evening. Where's the room? Remember that awesome orchestra, K-pop dance, and rock concert? The one from 6 to 8:30 that donates all the proceeds to charity? Yeah, sure. Where's the Roof is on next Tuesday evening. Don't forget to buy tickets and grab a friend to come along. QR codes are found on posters across the school, and the link to purchase is on the K-pop Dance Club and Service Club Imagine Instagrams. Be there. This is another Christian announcement. We're meeting tomorrow morning at 7:10 in the team room. We're having a teacher Q&A, so make sure to come with questions. And there will be donuts, so be there.
Hey Knocker, this is an HSU announcement. We have a very special meeting tomorrow in room 2701 at 7:20.
We will be having a speaker come in and talk to her experiences as a Latina in the medical field, as well as her immigrant experience here in the United States.
So don't be late. If you want any more information, there's on Tonka HSU on Instagram, so be there.
Good morning, MHS. My name is Matthew Wadman. I'm a senior this year, and I've had the opportunity of serving in the new admin intern position this year. The admin team is looking to hire 2 new interns to fill my position to work over the summer and into the next school year. The admin intern is a critical role on the MHS leadership team, and the person in this position works with key leaders at MHS to build culture and enhance student belonging. An ideal candidate has a passion for building school spirit and communicating effectively with the student body and other staff members. We are now accepting applications, and all current sophomores and juniors are encouraged to apply. Please check out the link in Mr. Erickson's Instagram bio for more information. Thank you and have a great day.
Good morning, welcome back to another exciting week of activities updates. We're your hosts,
The notorious Bowie B.
and Lil Lucas Berg.
Skipper Student of the Week is Catriona Trin, a junior for robotics. Catriona recently won the 2022 Affiliate Award for Aspirations in Computing. Over 3,500 students applied in the state of Minnesota alone, so it's a special award to receive. Catriona is a vital member of the robotics team, especially helping out with our outreach and community connections. The robotics team is grateful for all of Catriona's hard work. Congratulations to Catriona.
Another Skipper Student of the Week is Aria Dev, a senior for speech team. Aria led the speech team as captain and has been a great role model and leader of the team. Aria also recently qualified for state and will represent our team on April 22nd. Congrats, Aria, and good luck.
Skipper Artist Student of the Week is Rose Leary for Literature Magazine / Pretty Words Club. Rose is the calm center of the storm that is Pretty Words Club and Lit Magazine. She is both an excellent writer and a wonderful human being. Rose has a way of bringing people into her orbit and making them feel welcome. Congratulations, Rose.
And remember,
Stay classy, Skippers.
Hi, this is a message for any students who speak Somali. This is a really exciting opportunity. It's for 10th, 11th, or 12th graders. If you can speak, read, and write in Somali, Ms. Jordan and I have tracked down an exam that you could take that can qualify you for the bilingual seal, maybe get you some college credits, and get that skill on your transcript as a huge asset. So please see me, Mrs. Siegel, or Ms. Jordan if you would like to take an assessment in Somali and potentially earn bilingual seal and college credits. Thank you.
get down.
Awesome. So just a quick few announcements. First of all, I'm not sure if you know that today is Tornado Awareness Day, and so consider yourself aware. And then at 1:45, there will be a drill, and you'll be heading out into the different areas of the building, and it'll take a few minutes to take care of this tornado awareness activity, and t-shirts will be available in the comments. Second piece is just a note that for seniors, if you have any interest in being part of the music lab, please let me know. Matthew Wadman gave a great announcement about the intern opportunity. So I will be sending out in your student email the job description and the requirements requirements, basically you need to produce a resume and a letter of interest, send that back to me. I just want to emphasize how important that role has been. Some of those popular photos that have ever been displayed on Instagram have come through Matthew, and so we're excited about this opportunity and having two people doing this work. So please take a look at that. Lastly, in my Sunday night email, I want to make sure we're clear about attendance. As you've noticed, we really focus on unexcused absence. Logically, you need to be in school. You need to be in school on time, and if it's unexcused, you know that we'll be reaching out to you to figure out what's going on. And then also that you know that when you hit a certain number of unexcused absences, that you could be dropped from a course. So the big thing is you need to be in class, on time, engaged. It's not an encouragement, it's an expectation that you're doing that. So with that, enjoy Tornado Awareness Day. Have a great day.
Okay, good morning. Forget when it was a long time ago. We actually had a tornado drill, and we all went out into the hallway, and when we were out there, a tornado siren went off. And we literally had to sit out there for like half an hour. It was the craziest thing. But hopefully we won't have that today. All right, those people in the back, come and have a seat in your desk. You need your iPad today. And we're going to continue with our unit called K&Ts. So in today's folder, you'll find a file that'll say try these temperature and another one that says try these pressure. One should look first like this on the top. Temperature, we'll define that in a second, but let's first just watch this short little video.
You wouldn't stick your finger in here to see how hot it is. And fortunately, you don't have to. Thermometers measure temperature for us. But how do they work? There are several different kinds of thermometers, but most consist of a thin tube filled with a liquid like mercury. As mercury is heated, its molecules gain kinetic energy and move farther apart. So the mercury expands and rises in the tube. As it gets cooler, the molecules lose kinetic energy and move closer together. So the fluid contracts and falls in the tube. The numbers along the side of the thermometer are keyed to one of three temperature scales. The Celsius temperature scale, which is used in most of the countries of the world, the Kelvin temperature scale, which is used in science, and the one most Americans are familiar with, the Fahrenheit scale. Water freezes at 32 degrees Fahrenheit, at 0 degrees Celsius, and at 273 degrees Kelvin. Water boils at 212 degrees Fahrenheit, 100 degrees Celsius, and 373 degrees Kelvin. Which scale do you think is part of the metric system?
Celsius.
The Celsius scale is used to measure temperature in the metric system, and there are exactly 100 degrees between the freezing point and boiling point of water, while the difference is 180 degrees on the Fahrenheit scale. Now that looks cold, but thanks to thermometers, we can find out how cold it is without having to be out in it.
All right, temperature, let's define it first. Now, temperature is not heat. All right, that's a confusion sometimes. It's like they are related. Heat is energy, and we measure it in joules, and you can add heat, take away heat, and things will change temperature. But temperature is not heat necessarily. All right, so temperature is actually measuring something about the kinetic energy of the molecules. Remember yesterday we talked about molecules always flying around, and each one of those molecules has a kinetic energy, 1/2 mv squared. And if you take the average, because some are fast and some are slow, then you're arriving at temperature that way. We're not going to go into calculations like that on there, so we'll just take this as a simple definition. All right, you might see a definition like that on the test if you want to make a little note. What is temperature? And temperature is not heat. Just keep that one in mind. All right, they in the video talked about these kind of old school thermometers, and most of you are probably familiar with that little tube, and then In the old days, we used to put mercury in there, and when it heated, it would expand and then it would go up and down the tube. And you measure temperature. Then we figured out mercury's poisonous if the thermometer breaks and so on. So now we have thermometers that have alcohol in them, like rubbing alcohol, and it works the same way as well. All right, but probably even more better nowadays, just a digital thermometer like the ones we use in the lab. You just put the thing in there, it tells you the numbers straight up. But you still see these around once in a while, temperature scale. Now, let's talk about the different temperature scales. All right, one of the first scales was made by Lord Fahrenheit, and that's the one we're most familiar with in the United States. And we are one of only a couple of countries that actually use that temperature scale. And when Fahrenheit came up with the scale, kind of arbitrarily picked a number to call 0. All right, and you can, of course, as we know here in Minnesota, you can go below 0 and you can go above 0. And at the time, no one really knew what the limits were on that, so it just kind of, well, let's just pick any spot to call 0, and then we'll increment it from there. And we don't know for sure, but I think the reason why he picked 0 at that temperature was probably the coldest artificially produced temperature at the time. Because remember, we don't have refrigerators and things like that. So the coldest temperature you could make, like in the lab, would be to take some water, put a bunch of ice in it, add some rubbing alcohol and some salt, and stir it around, and it will get really cold, much colder than normal freezing temperature of water, and I think that's what he called 0. All right, so water freezes at 32, but you can get colder than that, and I think that's what he picked for 0. And then you just increment up and increment down with seemingly no limits to it on there. So that was one of our first scales. And then Celsius develops a scale that's a little different, and he says, well, let's make the normal freezing temperature of water, we'll just call that 0. All right, because that's a very distinctive temperature, and you can, have temperatures above it and below it. And then he also says, well, let's make 100 be the boiling temperature of water. So you got the freezing temperature of water and the boiling temperature of water, and then we'll just split it up into increments in between, and that was his reference spots. So it made a little bit more sense. It was a reference to something. I think on the 100 here might have been close to what he thought was normal body temperature. All right, it was 100, which we know now is 98 degrees, so pretty close to what he had for 100. And it might have been something related to that. We don't really know for sure. All right, and then we end up having the Kelvin temperature scale after Lord Kelvin, and that one is closely related to the Celsius scale, except at some point along the way we figured out that there is a limit to how cold one can get. And remember yesterday we talked about molecules always moving around and stuff like that, and if they slow down, they get colder, or when they get colder, they slow down, and when they stop moving, they can't get any colder than that. So that would be as cold as anything could get when all molecular motion stops. So Kelvin said, well, that's what we should call 0, because that is the coldest temperature you can get. So we sometimes call it the absolute temperature scale. And there are no negatives. You don't go below 0 in Kelvin, not possible. And he made 1 increment of Kelvin equal to 1 degree Celsius. So they're kind of related to each other as well on there. And then seemingly no limit to how high you can go on there, but the coldest you could get would be 0. And we call that absolute 0. All right, so when we mean absolute 0, that's the coldest possible temperature anything can get. Kind of on a theoretical basis, because you couldn't really measure something that's at absolute 0, because any kind of measuring device is going to probably add heat to the thing that you're measuring. So we sometimes say it's a theoretical limit, because we couldn't really have it and measure it at the same time, but we know what it is. If you translate between the other scales, then your Fahrenheit and your Celsius go below 0 to hit that absolute lowest temperature you get. In Fahrenheit, it's minus 460, and in Celsius, minus 273. So those are our 3 temperature scales, and you see them in different places. In the US, most often Fahrenheit. In any other country, you probably measure your temperatures in Celsius, and the Kelvin scale is more of a scientific thing. Just in science, you'll probably hear that. And later, when we do calculations with pressure and temperature and stuff, we will have to use the Kelvin scale. Right? Also, note this, that Kelvin does not have degrees. So you don't say 100 degrees Kelvin. right? Because it's an absolute scale, it's not measured based on an arbitrary number, it's based on the real zero. So it doesn't have a degree symbol to it, whereas the Celsius and Fahrenheit say degrees, all right, for that reason. So we say it's 373 Kelvin, and we abbreviate with just a K, but don't put a degree symbol, that would not be technically correct. Right, to convert from one to the other, you can just do a little bit of algebra to do that, and on the test, we'll do a little bit of that. When we are in the lab measuring stuff, we usually measure it in degrees Celsius. That's what our thermometers will do, and then to do calculations, we gotta convert it into the Kelvin scale before we can do calculations. All right, we'll probably put that formula right on the test, and you got a quiz coming up too that you'll have to do some converting from one to the other. So those are our 3 temperature scales, and all 3 of them are used in different places around the world. A lot of you probably have traveled to other countries, and if you're like on a cruise or something like that, the captain will come on and say, "Oh, it's a beautiful 23 degrees today," and that would be in Celsius for you Americans, and that would translate to about 82 degrees outside in Fahrenheit. All right, some key temperatures that I want you to remember. If I say room temperature, all right, Karina, what do I mean? What's room temperature?
The temperature in the room.
Temperature in the room, correct? How many degrees would that be, Fahrenheit?
It depends, but probably around like 68.
68, that is correct. All right, now, when we say room temperature, generally that's what we mean, 68. Most people set their thermostat in their house to right around 68. Now, some people say, I like it warmer, I'm gonna set it to 70, and some people say, oh, I like it really warm, I'll set it to 72. So, but when we say room temperature, sometimes like when you're cooking and stuff, they say, let the butter get up to room temperature, right? That's what we mean, and if whatever your temperature is set at, it's not gonna really fluctuate a whole lot from that, but that's what we mean. Convert that into Celsius, and that's 20 degrees. So generally, if we say room temperature, well, that's what we mean. All right, let me look at my thermometer here and see what it says right now. It says 22 degrees. All right, probably because I was holding it for a little while, then it's a little bit warmer. And if I let it sit, all right. And then we got normal body temperature. Gus, what is that?
I'm not sure.
You take your temperature, and if you're normal, what would it be?
98.
98, that's correct, 98 Fahrenheit. All right, 98 degrees Fahrenheit, translate that into 37 Celsius. All right, if we say you have a fever, what does that mean? That means your temperature is above 98. All right, I got a low grade fever, I'm 99, maybe 100. All right, not so troublesome, just means you're probably sick and your body's fighting off some disease, and help do that, it heats your body up. All right, if you get a really high fever, something like 102, that's kind of disconcerting, that's getting pretty high on there. If you hit a temperature of about 104 degrees, that's time to call the ambulance, because that could be dangerous. All right, temperatures of 105, 106 degrees Fahrenheit probably kill you. All right, it'll destroy your brain. So if you get above 104 degrees, that's a serious business. All right, you go into a cold shower or something like that, cool you down a little bit. All right, because that could start to do damage to your brain cells getting too hot like that. All right, so none of you probably had any temperatures higher than, anybody been at 104? Some of you have? It's kind of miserable feeling because, you're real hot and sweaty and like that. And different people might be able to tolerate it a little bit more. All right, boiling point, or melting point, the normal melting temperature in Fahrenheit is 32 degrees. So if we say it's freezing outside, what we mean is it's colder than 32 Fahrenheit, because that's the temperature water freezes. All right, when I left this morning, it was 34, and it was raining, not snowing, because raindrops hadn't froze. All right, if it drops just a few degrees, then the rain will probably turn into snow. It is possible to snow when it's 34 degrees, because way up there the temperature is colder. By the time it gets down here, maybe it hadn't melted yet. So at 34 degrees like it is today, you're kind of teetering right on the edge of either rain or snow, like that. Translate that into Celsius, and we're talking 0 degrees Celsius. Water boils, you get water, and it will boil at 212 in Fahrenheit and 100 in Celsius. Now, we say the normal melting point and the normal boiling point because that could change based on a couple of things. One, pressure. As the air pressure goes up and down because of weather or altitude, that boiling temperature and melting temperature could change as well. So it's related to that. Here in Minnesota, we're a little bit above sea level, so our boiling temperature generally is a little bit lower than that 100 degrees, all right? Quite common that in the lab, we do some lab and the water boils at 99 degrees, maybe tomorrow, 98 degrees. That depends on the air pressure. If the air pressure drops, then that temperature will be a little bit lower. If the air pressure is higher, that temperature will be a little bit higher. And weather can affect that. Go to Denver, Colorado, and the normal boiling temperature there is 95 degrees Celsius, just because Denver is much higher in altitude than we are. All right, so these are for at sea level. That would be your average temperature there. So those are some key temperatures that you kind of remember. All right, on the test, we'll do a little bit of converting. We'll give you the formulas for doing this. Let's look at a few examples. This first one's here, we might not have to actually calculate, but 0 degrees Fahrenheit, colder than the freezing temperature. All right, to convert that, I would do this. I would take my 0 degrees Fahrenheit minus 32, and then multiply it times 5, divide by 9. All right, that's how I can convert. So 0 degrees Fahrenheit translates into negative in Celsius, negative 17. So we can just use the formula to convert from one to the other. 32 degrees Fahrenheit, hopefully you remember that. That's that freezing temperature of water, which in Celsius is just 0. We just kind of remember that one. 68, that sounds like normal room temperature, which will translate into 20. And then we got body temperature and boiling temperature. Right, those are our key temperatures we just talked about. To go 80 degrees Fahrenheit to Celsius, I'm going to take 80 minus 32, multiply times 5, divide by 9, and we could convert. Right. We'll do a little bit of practice with that. That requires a calculation. So the test, we'll probably have a couple of those on there. The main conversion that we'll probably end up doing would be converting from Celsius to Kelvin. See, you got an error here. I put degree Kelvin on it. That's not going to be correct. All right, technically it should just be K, not a degree K. Since it's not a relative scale, it's an absolute scale. Now, in the lab, if we measure temperature, it's probably going to be in Celsius. And if we use that to do some kind of calculation, like we'll talk about tomorrow, we got to convert that into Kelvin. So all you got to do is take your Celsius, add 273, and that's it. Going from Celsius to Kelvin is easy. Just add 273. So if we ever do calculations with temperature, it's got to be in Kelvin. Something to remember, but I'll remind you a lot of times. On the agenda, there's a worksheet and a quiz. Yeah, it's just going to do that kind of thing right there. We'll practice a little bit. All right. Vaporization. What does that mean? That's when you take liquid, turn it into vapor. Like evaporation is vaporization. Evaporation just kind of happens at room temperature. Only certain molecules. Vaporization. I remember yesterday we talked about molecules moving and they have kinetic energy, and some of them are fast and some of them are slow. And if any of those molecules get fast enough, they can literally jump into the vapor phase. Let me show you this little clip again that we looked at yesterday. All right, vapor pressure. Let's just use water, that's the best example, I think. Normal air is a mixture of different gases. You got some nitrogen, oxygen, and small amounts of other stuff. All right, normal fresh air would be that, but that other stuff could change, all right? Especially water is included in the other stuff, water vapor. And if there's a lot of water vapor in the air, we call that high humidity. And the percentages will all shift then if that were the case, like that. So what happens is when water vaporizes, it turns into a gas and it pushes on the air pressure like that. And the warmer the water, the more water vapor wants to evaporate. Right, so warm water evaporates faster than cold water does, and it contributes more to the air pressure when the water is warmer as well. So when you go to like the tropics, it's usually a lot more humid because it's warmer there. Now, if we made a graph of vapor pressure, so the vapor pressure is the pressure coming from the water, vapor coming off of there. As the temperature goes up, that gets larger and larger. So if we made a graph, it would probably look something like that. It just curves exponentially, increases with that. Now, once it gets, now that KPA, that's a pressure unit we'll talk about later. Don't worry about what that means just yet, but KPA means kilopascal, and that's a way to measure pressure. Here's what we're talking about. In a liquid, the molecules moving around, they can move, change shapes, but every once in a while, one of them gets fast enough and breaks free and goes flying up into it becomes a gas, basically. So here's your liquid, and now these things are evaporated and turned into a gas that just kind of fly around, right? Some of them are moving fast, some moving slow. Eventually, at some point, one will get fast enough and just jump right off. Right? There's intermolecular forces pulling between these molecules, holding them sort of together, but they're not really strong bonds, so they're fairly easily broken, and then stuff can vaporize. So if a molecule gets that amount of energy, then it can jump right off the surface. Here's a graph, a more precise graph of what I was just talking about there. On the x-axis, it's got pressure, on the y-axis, temperature, and this is the vapor pressure from water. And you heat water up, the vapor pressure of it continues to rise and rise more and more. Once you get to the normal atmospheric pressure, then that's the temperature at which water is going to boil. All right, so if the pressure changes, then the temperature of water boils will also change. And you can look at that graph to see what it would be. Specialized pot. Anybody see one of those? Jacob, you ever seen one of them kind of pots?
Yeah.
What are they called?
Crock pots.
Actually not a crock pot, but it's called a pressure cooker. Pressure cooker. Crock pots are, a little different. But this one has a pressure valve on it, and the lid clamps down really tight. So when you start to heat it, the pressure builds up inside. What's the purpose? As the pressure builds up inside, it will make the water boil at a higher temperature. So the purpose of this kind of pot is to make water boil at a higher temperature. Basically that, pressure cooker. There's some popular ones now, they're called Instapots. Anybody have one of those? Instapot? They're getting kind of popular. Why would you use such a thing? If you can make the water boil at a higher temperature, you can cook faster. So you want to make a stew or something with an Instapot, it might take 20 minutes, where on the stove it might take an hour and a half. All right, so you're just increasing the temperature at which water boils. It's got a valve to tell you what the pressure is, and it's got a little scale thing there, and then a release valve, pressure release valve. Because if you didn't have a pressure release valve, it could build up so much pressure the thing would literally explode like a bomb. But they have that built in on the Instapots and stuff, so they're very difficult to make it explode, but they could. And they tell you in the directions, make sure you check that valve doesn't get plugged up. If it doesn't make a weird sound and steam coming out of there, then that thing is plugged up. And they'll tell you, right, Instapot will just automatically shut off. This pressure cooker doesn't have an automatic shut off, it's an old school one. And you use it to, make stuff cook faster, for one reason, and make water boil at a higher temperature. If you live at a high altitude, like in the mountains, you might want to use one of these because, well, that water boils at such low temperature up there. And like that. So that's what that is. All right. So the boiling point of water then depends on that air pressure. Right now, we got certain air pressure, which we'll talk about in a minute, and that will determine what temperature water boils at. And that fluctuates just a little bit on a daily basis. Right now, we're in the middle of a storm, so our air pressure is kind of low. And once the pressure starts rising, we know that good weather is coming. So probably later tomorrow, that'll be the case. If you went to the top of a high mountain, like this is Mount Kilimanjaro, this is in Africa. You go to the top of that mountain and water boils at a really low temperature, you could probably dip your hand right in the boiling water and it won't even burn you. When you go to a really high altitude, because the air pressure is so low. So in which case, if you lived up there, you probably have a pressure cooker, otherwise you wouldn't even be able to cook your food. It would take, 3 hours to cook some spaghetti because the temperature is so dang low at that high elevation. All right, then again, that's in the temperature. All right. So that's a little bit about temperature. Number 2 then, try these. Pressure. Let's talk about pressure then. Should look like that. So first, a little bit of vocabulary. Gas pressure, like air. Air is a gas. Air pressure is a gas pressure. Why do we have pressure anyway? Remember, molecules are flying around, bouncing off of everything, and when they hit stuff, they push on it. So the force from air pressure is from the air molecules colliding with stuff, like you, all right? And those air molecules are bouncing off of your eardrums, and if the pressure goes up, it's going to have an effect on your eardrums, and most of you probably have experienced that before too. A vacuum is just a space that has no gas molecules in it, right? We call it a vacuum. A vacuum cleaner is a container that you suck the air out of and then all the dirt goes in there. All right, so a vacuum cleaner uses a vacuum. A vacuum is a technical term, scientific term, where there's no gas pressure. When you go out into space, like outside of the space station or something, we say that's a vacuum because there are no gas molecules there, at least very, very little amount of there, so the pressure is really, really low in space. Atmospheric pressure, pressure from the atmosphere, that's the air that we breathe. That can fluctuate day to day. It can fluctuate based on altitude as well. To measure air pressure, you use a device called a barometer. A barometer. Sometimes you watch the weather and so they say the barometer is 29 inches and rising. All right, that 29 inches is measuring, we'll talk about what that meant, how that came about. And the fact that it's rising is a clue that the weather's going to get better. Right? So I think when we looked up weather right now, we'll probably see the barometer is rising as the bulk of the storm has passed by. There's different kind of barometers that we use to do that. We'll look at a couple here. All right, that's a little bit of vocab. All right, fluid pressure versus air pressure. Now, air pressure comes from air molecules hitting stuff. Fluid pressure comes from fluid molecules. Simplest example, water. All right, now, most of you probably have been diving into water. You go in a pool and you go down to the bottom of the deep end and it kind of hurts on your ears. All right, who knows what I'm talking about? All right, that's because of the fluid pressure. It pushes on your ears. The deeper you go, the more it pushes. The same thing happens in air, except you gotta go up and down a lot further than you do in water because air is a lot thinner than water is very dense. And most of you probably experience, you go up in an airplane and your ears pop. Because when you go higher and higher, the air pressure goes down. Right now in this room, the pressure inside your head and outside of your head are equal. So your eardrums, can move around just as they're supposed to. But when you go up into an airplane, the air pressure gets thinner, and now the pressure inside your head is bigger than outside, and your eardrums bulge out. And they don't wiggle as much, so you can't hear quite as well, and it's kind of irritating and hurts. And then all of a sudden, boop, it pops, and the pressure equalizes, right? What makes that happen? There's little air bubbles inside your ear, and it will come out through a little hole. And then your eardrum pop, and then back to normal. And then you come back down, and now you're going from low pressure back to high pressure, and your eardrums are bulging in. And the same thing happens then. Right? So when your ears pop, that's an equalizing of the pressure inside and out on your ear. The same thing can happen when you're diving into water. Anybody certified to go scuba diving? All right, when you learn how to scuba dive, all right, you go down just 10 feet in the deep end of a pool, and it hurts quite a bit. But if you stay down there long enough, what happens is that water goes inside of your ear. And then the pressure equalizes on the inside and outside. All right, so you dive down in there, and literally your water has a little valve, a little hole, and the water can go in your ear, and the pressure gets equalized. Then it doesn't hurt anymore. If you go diving like 500, 100 feet down into the water, if your ears couldn't equalize like that, it would destroy your eardrums. It would literally just break your eardrums, and then it would wreck your ears. So your body has this ability to sort of equalize the pressure in and out of your ear. This is why you swim underwater for a while, you get out, and I got water in your ear. That's because it's supposed to, because you've been underwater and it's equalizing. The further down you go, the more that's going to happen. And if you take scuba diving lessons and stuff, they kind of teach you about that and how to deal with it. Some people, can equalize the pressure a little bit easier than other people, but that's just a mechanism that your body can do so that you can swim in water and not destroy your eardrums. Same thing when you change in altitude as well. And also, air pressure changes just because of the weather, and sometimes that change isn't so drastic that your ears will pop, but in some cases, when a cold front comes in, people are like, oh, my ears are kind of plugged up. You get that sort of feeling. It doesn't usually hurt, but then all of a sudden it will equalize, and your ears will pop, and the pressure will equalize. So when you go up in an airplane, that's kind of a lot more extreme as well. We may talk about diving a little bit more later too. So where is the highest spot on the Earth? Emilio, you know where that is? Mount Everest. That is the highest spot on Earth. Mount Everest, 33,000 feet. All right, when you go up there, the air is very thin. On your way up, your ears are going to probably pop a few times. And when you get up to the top there, the air is so thin, it's really hard to breathe. People that go mountain climbing to the top of it, that last 200 or 300 feet is literally, the air is so thin, they just like, take 3 steps, catch your breath, take a few more steps, catch your breath. Right, if you've ever been in the high mountains, you know what I'm talking about, all right? If you go to the top of Mount Everest, most people have to bring air with them. It's like a scuba diving tank, basically. And you just put it on, and you've got to bring your own air if you're going to go that high. And people that mountain climb, they bring tanks. They're not really huge, they're about this big. And then on the path up there, there's literally bottles laying all over the place because people just throw them away and then they come back down like that. There are some people that live in the area that are used to it, and they could probably climb almost the top, don't need extra oxygen as well. So that's the highest spot on the Earth. The lowest spot on the Earth would be below sea level, and that's here along the Dead Sea over here in the Middle East, right? And this used to be kind of an ocean, and this is the ocean here. When you go from the ocean over to this little lake, you're going downhill. That's in a valley. And it used to be a lot bigger, but it's drying up, and there's just a little bit of a lake left. It's still not dried up yet. But that is the lowest spot on the Earth. And when you go down there, your ears are going to probably pop a few times by the time you get down there. And the air is very high pressure and thick. Sometimes people literally go there that have breathing problems because the air is much thicker and denser there. It's a little easier to breathe. So sometimes people will just go there and just have a vacation for a few days and breathe nice and easy there because the air is so thick, more so than anywhere else. Right here in Minnetonka, our elevation is 889 feet above sea level. So if you go from the ocean, you're going uphill to get to Minnesota. And we're at about 889 feet above sea level right here. That now. So we're not nearly as high as Mount Everest, but we're not, in the valley either. We're above sea level. Take a look at this map. This is a map of all the rivers that flow into the Mississippi. And water always flows downhill. So all of these rivers, including the Missouri and other ones, they just all flow into the Mississippi and then right into the Gulf of Mexico. Right, like that. So all of this stuff is above sea level. So as you're going from here up to Minnesota, you're going uphill and the water flows downhill. Like that. These are just the rivers that go into the Mississippi. If you're over here, these rivers, which they don't show, they all flow into the Pacific Ocean. All right, we call that the Continental Divide. Have you ever heard that term before? That's just the highest spot along this ridge. Any rivers on that side flow this way. Any rivers on this side flow this way. And most of them probably flow out the Colorado River, which goes out way down here somewhere. So any rivers on this side would flow this way. All of these rivers flow this way. Any rivers here would flow out that way somewhere. And right here you can kind of see there's a line that goes right through Minnesota. That's the Continental Divide in Minnesota. If you go to any river on the other side, like in the Boundary Waters, those rivers flow out of the Great Lakes into the ocean. And then there's another divide up here. Any rivers up there flow into Hudson Bay. So there's actually 3 ways where our water goes in Minnesota. Most of it will go into the Mississippi and flow down to the Gulf of Mexico. Like that. So when they say the Continental Divide, that's what they mean. There's actually 3 divides in Minnesota. One that flows into Mississippi, another one that flows out the Great Lakes, and another one that flows into Hudson Bay. It literally flows north. There's I think it's called the Red River. It's out by Fargo. And there's a certain spot on that river that can actually stop and flow the other direction because it's at the top of the divide. All right, I don't think it switched direction for a while, but all right, so that's that case. Now, and you can see Mississippi starts, hopefully everybody knew that Mississippi starts up here in Minnesota. Has anybody been there? The start of the Mississippi? Yeah, it's kind of a cool place to go. You go there and there's this pillar here. And on the pillar it says, you're at 1,475 feet above sea level. That's the start of the Mississippi. And then it flows downhill to the Gulf of Mexico and a whole bunch of rivers join into it. Right? When you're up there, the river is really nothing more than just a little creek. Right? Here's a lake called Lake Itasca, and the river flows out of that lake, and that's the start of the Mississippi right there. You can literally walk across it. It's very small. So then as different streams and rivers flow into it, it gets bigger and bigger. By the time it gets to Minneapolis, it's pretty wide. When you get down to New Orleans, where it dumps into the ocean. So here's what it is at the start, just a little creek. You can take a canoe down it. And then once it gets to New Orleans, it's super wide because of so many rivers have joined into it. You can literally drive ships in it and stuff. And then it flows into the Gulf of Mexico. And that is at sea level then. Everything's down at sea level. All right, that's a video. We'll save that for a moment. All right. So what is pressure? If you're in physics, you would do pressure like this. We probably won't use this formula, so if you don't write it down, that's right. Okay. All right. Force is a push. And then area, square meters or inches or something like that. So pressure is force divided by area. Force divided by area. So when you stand on the ground on 2 feet, there's a certain pressure underneath your feet. It's your weight divided by the area of your 2 feet. If you stand on 1 foot, it's a lot higher pressure underneath your foot because now all your weight's divided by 1 area of 1 foot. If you stand on the tip of your toes like on a ballerina, the pressure is enormous because all of your weight is spread over a very small area. Very small area. Very high pressure. So what does air pressure come from then? It comes from the air molecules being pulled down because of gravity, and when you're at the surface of the earth, the pressure is the highest. The higher you go, the air gets thinner and thinner and thinner. Once you get out to space, there's no air left at all. You won't be able to breathe in space. All right, a little bit about units. Newtons divided by meters is what we call Pascal. If you wanna make a note, that's the unit we're gonna probably use. Pascal. It's a unit for measuring pressure. We abbreviate it with a PA, capital P, lowercase a, Pascal. Normally, we would probably use kilopascal, but we'll see here in a minute. All right, that's just one way to do it. We could also measure pressure in what's called atmospheres. At sea level, you're at 1 atmosphere. And that can fluctuate. You know, on one day it might be 1.2, another one 0.99, but that's the average pressure at sea level on an average day, 1 atmosphere. People that go scuba diving, they usually measure pressures in their tanks and the water pressure in atmospheres. It's a different way to measure it. All right, how do you actually measure pressure? I think now we did talk about this a while ago. If I take a test tube like this and I put it into this trough of water so that all the air is out of the test tube, I can tilt it upwards and that water stays inside. If I lift it up, the water flows out. All right, I could also do this, take the test tube and a little beaker and set it up like this. And the water stays inside the test tube. If I pull this out, the water again will drain out. All right, why does the water stay in there? It's because of air pressure. Air pressure is pushing down on this surface, holding the water up the tube. It literally holds the water up the tube. And the question then, how tall a tube could you get? Because there is a limit to our air pressure. It does fluctuate every day. Right now it's probably around 14.7 pounds per square inch, which we'll talk about here in a second too as well. So the highest tube that I can make this work would be about 34 feet. All right, this tube is much shorter than that, so that would be the highest tube that you could do. All right, if a tube was any higher than up here, what you would have would be a vacuum, where there's nothing. Might be a little bit of water vapor in there, but a vacuum. And the air pressure can fluctuate on a day-to-day basis. It can fluctuate because of altitude. So this air pressure pushing down on here can make this level go up and down a little bit. If the pressure goes bigger, then the height gets taller. If the pressure drops, then the level will come down a little bit. Now the first barometers that we did with this used, instead of water, used mercury, which is much more dense, and the tube doesn't have to be so tall. Right? If you did this with mercury, it would be about this tall, 700 millimeters. All right, and it'd be manageable then. This 34-foot tube would really not even fit inside of a room, but it will for mercury. So the first barometers were that, mercury barometers. They look like this. And we used to have one of these. We got rid of it a while ago because mercury is poisonous and we don't like it in school anymore. But it basically looks like this. This is a thin tube, and you put it inside of this little casing here, and all we need to look at is the top. And it goes up and down and up and down, and then it can tell us that the pressure is changing. It's about that tall. You bolt it to the wall because if it tips over, the mercury will spill out of it. That was our first barometer. That was invented by Angelisto Torricelli. That was our first barometers. Okay? And we used them for a long time. Right? Only recently did we get rid of those kind of barometers. The other kind is what we call an aneroid barometer. How does that work? Basically just an accordion that as the pressure goes up, it squeezes it. Pressure goes down, it expands. And then you stick a little gauge on it and that will go up and down. No mercury required. It's just like an accordion, and the pressure squeezes it, the pressure expands it, and so on. So that's how we measure pressure. You don't need anything. Here's an old school recording barometer. We used to have these things around. Here's your squeeze thing, hooked onto this lever that would go up and down. It has a pen on it. And this whole drum will spin really slow. Each line is 1 day. So next day it's going up, next day up, up, down, down, down. You can see some lines that spun around a few times. And the pressure is going down, pressure is going up. So the pressure changes every day, just a little bit, and this can tell you if that line is going down, the pressure is dropping, bad weather's probably coming in. If the barometer's rising, good weather's coming in. All right, some of you might have one of these at your house. On the wall, little gauge thing, one of them is a temperature, another one might be a barometer, another one might measure humidity, and I've seen a lot of people have those hanging on their wall. Like that, just a barometer, tell you something about the weather. A lot of you are probably familiar with this kind of a pressure measuring device, pressure gauge for like car tires and bike tires. Put it on a little valve and then the thing pops out, you can read what the pressure is. We say pressure gauge because all it really measures is the difference in pressure on the inside and outside of your tire. All right, when your tire is empty or not pumped up, the pressure inside is exactly the same as the outside. Or when you pump up the tire, then the pressure inside gets bigger than outside, and that's what you're measuring. All right, with a pressure gauge, differences in pressure. All right, standard pressure. This I want you to write down because we're going to utilize these for some calculations. Now, if you recall back when we did stoichiometry, we always talked about STP, standard temperature and pressure. What is that? Standard pressure is the average pressure at sea level. At sea level. If you had this kind of barometer at sea level, on an average day, it would be 760 millimeters tall, that column of mercury. And it will go up and down depending upon the weather. If you go to higher altitudes, then that level will come down, and so on. So by standard pressure, that's what we mean. Then you could translate that. Now, note this, that millimeters doesn't measure pressure, it measures length. So when we say that, we've got to say millimeters of mercury for it to really make any sense. Right? Because millimeters doesn't measure pressure, it measures height. But the height can be translated, so using a mercury barometer, you'd say millimeters of mercury. HD is a symbol for mercury. We sometimes just call that a torr, after Torricelli, the guy who invented it. Of course, we could convert that into inches. So if you ever watch the news and they'll say the barometer is 29 inches and rising, they'll tell you that rising tells you that the weather's probably going to start getting better. When the barometer rises, good weather's coming. When the barometer falls, bad weather's coming, generally speaking. We could translate that into pascals, but most commonly kilopascals, or atmospheres, or if you're doing a bike tire pressure, pounds per square inch. So all of these pressures are the same thing. They're just different units of measuring. Right? Kind of like I can measure in inches or I can measure in feet. It's the same, measuring the same thing, but in different units. On the test, we'll probably give you a chart that looks like that. There are a couple other ones too, but we're not going to go any further than these 5. I'll let you know, but I don't think we will. They all are equal to each other, so I could use these to convert, and that is something that you will do on the test and on the quiz that you're going to have here in a little bit. As soon as I stop talking, I'm talking too much. But let's look at a couple of people. There's the guy who invented it. All right, here's a sample test question. I got a pressure of 635 millimeters of mercury. I want to convert it into kPa. All right, we do this kind of like you do stoichiometry. Start with your given, make a ratio, any two of those two things. I got millimeters mercury up, millimeters mercury down. 760 came off the chart. And I got kPa up because that's what I'm looking for. Anything on the top, multiply by, anything on the bottom, divide by. And you can convert from one unit to the other. So, first simple piece of the test, that's what you're going to do. And we've already kind of done this with other things too, so it's not something new. But converting from one pressure unit to the other. And we do that quite a bit. When we go calculations, there's a special unit that we'll want to probably be in. We probably calculate with kPAs. So if we had something other than kPa, we may have to do a conversion on your problems, and I think most problems are going to probably involve some kind of conversion. Let's started off. But that's pretty straightforward. Alright, that was a lot of business. I'm gonna stop at this spot. Third on the agenda says worksheet KMT. It's got stuff about gas laws that we haven't talked about yet, so. At this point, I'm gonna say work your way through page 1, that's your homework. The Schoology quiz, I think, has got a few of the same kind of questions. I haven't put the answer key, but I did put a little video on hints on how to do this, but I think everybody should know how to do that, hopefully. I know that's what you gotta do on page 1, basically just that. Or the temperature conversions, which we did a couple examples too ago. Did you guys talk about pressure in 9th grade? This stuff, KPA, millimeter mercury, various things. Maybe during COVID, we didn't do a lot of that stuff. How many people have used a tire gauge before? Few? Kind of an interesting thing to do. Maybe I'll bring a tire in here.
So I did this before class started. I kept getting these wrong. Is there a reason we do, I looked up conversions to just like see how to do it. Google says, 273.15. Is there a reason we just do 273 just because it's easy? Okay.